David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 2301 statics. This is going to be the third part. Try to break it into smaller parts. We're going to do the second example of a curve in a shape like this that's bounded by the y-axis. Remember, we're doing the moments of inertia by integration. And we're using this concept up here that we derived, that the moment of inertia about a rectangle about its base, an axis passing through its base, is bh cubed over 3. Okay, we use that for example 1, this triangle. Now we're going to use it for this shape, example 2, this curve bounded by y is equal to 8 and y is equal to 1 on the bottom. I'm given that this curve out here is a formula, x cubed y equals 64. So I just want to rearrange it and express it in terms of x, because I'm going to integrate it in respect to y. So just rearrange it. I get x cubed is equal to 64 over y, which is equal to 64 negative y to the negative 1. Take the cube root of both sides. I just get x equals to the cube root of 64y to the negative 1 power, which is equal to, the cube root of 64 is 4, and the cube root of y to the negative 1 is y to the negative 1/3 power. Because to figure the area of this thing, I want to use this horizontal strip of height dy, width x at any point on that curve. So A is equal to x dy. The area is then equal to the integral of that, dA, x dy. Plug in what I know about x. X is equal to 4y to the negative 1/3 power. Plug that in for x times dy. Evaluate it. I get 4 over 2/3 y to the 2/3 power. And I need to evaluate it from 1 to 8. At 1, this works out to be 6. If I plug 8 in for y, I get that this whole thing is equal to 24. 24 minus 6 is 18 millimeters squared. That's the area of that rectangle, which makes pretty much sense because it's 7 millimeters tall, and it goes from 2 to 4 wide. Say it's an average of 3, so the 7 times 3 would be 21, so I'm in the ballpark there. The moment of inertia about the x-axis of this shape is the moment of inertia. You know, I could use, if I could evaluate it, what I'm trying to do is get the moment of the spread of this area about this x-axis down here that it's 1 away from. So, break it up into a horizontal strip, use that same dA. The Ix prime goes to 0 because the height is dy, which is essentially 0, so I'm just left with the y squared, or dy squared, a term, or a dy squared term. So I just plug in what I know. Y squared dA is equal to y squared x dy, that's dA. Plug in what I know for x, which is 4y to the negative 1/3 power. Combining my y terms and bringing the 4 outside the integral sign, I get y as y squared times y to the negative 1/3 is y to the 5/3 power. So evaluate that. 4 times the integral of y 5/3 dy is equal to 4 over 8/3 y to the 8/3 power. Plug in the values of y at 1 and 8, and I get 384 and 1.5, so I subtract that and I get 382.5 millimeters to the 4th. Remember, all units of moments of inertia are something to the 4th power, some dimension to the 4th power. Okay, now I'm going to do this Iy, and because I'm bounded by the y-axis, I'm going to use that bh cubed over 3 value that I derived up there. So Iy is the integral of diy. and that is DIY is the integral of, or is base, or the length of the side along the y-axis, or whatever axis I'm taking moments inertia, which is y in this case, dy times its height, or in this case width, cubed. So it's dy x at any point cubed over 3 from this relationship of the moment of inertia of a rectangle about its base, or an axis that bounds it. So that's evaluated 1/3 times the integral 1 to 8 of x cubed, but x is equal to 4y to the negative 1/3, and I cube that whole thing. Keep on evaluating it. I get 1/3 integral 64, which is 4 cubed. Y to the negative 1/3 cubed is y to the negative 1 dy. So the integral of y to the negative 1 is ln, or natural logarithm, of y. And 64 over 3 is this constant term. Evaluated at 1, excuse me, the natural logarithm of 1 is 0, and the natural logarithm of 8 plugged in there times 64 over 3 is 44.36, so that's my answer, minus 0, 44.4 millimeters to the fourth. Okay, continuing on, just to show this part's easy, slam dunk. Polar moment of inertia is just Ix plus Iy. 3 to 2.5, 44, 427 millimeters for the fourth. Just adding those two numbers up. The radius of gyration, x, the x radius of gyration, is the square root of Ix over A. Just these values, 3 to 2.5 divided by 18, 4.61 millimeters. Ky, the radius of gyration about the y-axis, is similar numbers. You can see them, plug them in, do the calculation, 1.57 millimeters. Polar radius of gyration is Jo divided by A, that number divided by 18, 4.87 millimeters. So the key thing to remember is, whenever I'm doing an integral, I'm trying to find the moment of inertia about an axis that bounds it, I need to use that bh cubed over 3 number. Or you might look at it as b cubed h over 3, if you consider this b and that h. So when I'm doing a moment of inertia about that axis, I use that. When I'm doing the other one, the axis that it doesn't bound, or it's not up against, I use the y squared dA term. So that's the key to the highway to solving these kind of integration problems, is using this bh cubed over 3 term when I've got an axis bounding it.